And so we kind of just got to work on it. And we, again, didn't know anything. I mean, we didn't know what we were doing. We really didn't.
This footage is recorded on a Red 1 camera. This is a Redcode R3D file. I downloaded it from an old post from an open forum on internet. To play it, you need a Red's specific R3D player. To look inside it, I open it with a binary file viewer. At the first glance, it looks like a bunch of gibberish. But if you look closer, you will find some useful information, such as the file name that is encoded here, or the memory card this footage was recorded on, in this case Lexar 80A flash card, and the timestamp where the camera was running to record this. Nothing too special here, except in the header we see something like Dear Red 1, and in some intervals we see Red V. Each red V is a wrapper for one frame, so every time you see a red V, you know the next frame starts. And then there's RDA-O and RDA-S, that are the audio wrappers, although Red 1 camera could not record audio. And then there's this REOB that sits close to the end of the file, that seems like an end of file signature. So far there's nothing that interesting. But the interesting part starts when you look even closer. If you do so, you'll notice that ASCII representation of F-type sitting there. But why is this interesting? Looking at the guides to QuickTime file format, you will find out that QuickTime is made up of atoms. Atoms are constructing blocks of QuickTime files. As you can see here, F-type is one of the most famous ones. According to the format guide, the F-type atom was introduced as part of the standard specification in 2004, and so it appears in QuickTime files created since then. The next part is also important. This F-type is mandated to appear first in the file, one of very few atoms whose position is defined. Therefore, a player expects to see this at the beginning of the file in order to recognize that this is a QuickTime format. In the QuickTime file format specifications by Apple itself, we see what the next part is. Brand-specific features have a part ID that's one of the compatible brand codes for that file type, as specified in the file type atom or F-type. For example, the part ID for QuickTime specific feature is QT. That, in our red-coded R3D file, is JP2. That stands for JPEG 2000 format. In other words, when we are looking inside R3D file, we are almost looking at the JPEG 2000 standard file format in a QuickTime wrapper. If I download a normal JPEG 2000 file from internet, then obviously I can open this file in a standard viewer such as Photoshop. As you can see, JPEG 2000 file has superior quality to normal legacy JPEG. Even when I zoom in, I can still see details without any noticeable artifact. And when I open this standard JPEG 2000 file in the binary file viewer, we start to notice interesting things, such as this identical block size, the header signature, and the F-type atom, and its subtype JPEG 2000. So what if I remove this Red's added header? Here, I copied the content of the frame without the additional header, and I stick it into a new file. Now, if I compare the standard JPEG 2000 file header with this new file, they look identical. So if I save this extracted portion without the additional header into a new file and call it what is this.jp2, any standard file viewer, such as Photoshop, will be able to open it with no problem, with the exception of the colors. In fact, the bit stream for the colors are not correct. That's why we have all the detail and all the color information, but not in the right places. So when we are looking at the red R3D file, we are actually looking at a standard JPEG 2000 QuickTime video with standard F-type, brand ID of JP2, similar block size, and a standard JPEG 2 header. So the only reason a standard file player cannot play this one is that this standard JPEG 2000 QuickTime wrapper is wrapped inside a non-standard red made-up wrapper. So the player cannot determine the true nature of the file format. Funny enough, because decoding JPEG 2000 is CPU-intensive process, Red created and sold an extension card called Red Rocket to boost decoding on PCs. This card was sold for about $7,000. That's about 40% of the price of the camera. What Red didn't tell you was that this card was a pre-existing JPEG 2000 decoder board made by a German company called DVS Digital Video Systems. As Red's typical, they stuck their brand on it. This original DVS Atomics boards were shipped with controller cards for a fraction of the price. They also had different flavors for different use cases, such as HDMI and SDI. But Red didn't tell you. Red loves their customers, huh? So why should they? So if the inside of R3D is just a QuickTime JPEG 2000 file, how does Redcode work exactly? To get the accurate answer, we call the mothership.
I don't know, but anytime I see RM, N, GM, N plus, N minus 1, etc., and this is Graham's territory.
Is it RM and GM minus 1?
Yeah, it's basically some crazy math.
So RMN minus GMN minus 1 plus G, the inventor man says it's crazy math. Or is it? If you know how to add a few numbers together, bear with me. I'll show you how exactly Redcode works and what's its so-called patentable novelty. It's all here. This is a single cell of Bayer color filter array. There exist other filter arrays as well, but this is the most commonly used one. RGGB. To better understand Redcode, let's consider 4 of these blocks next to each other. So it gets you 8 cells in a row. Now consider 4 of them go in a column as well. It also gets you 8 cells in a column. We ended up with a 4x4 table of these blocks. But before moving on, should we pull the green information from the odd rows and group them together, and green information from the even rows and group them together, and group red and blue values together, we'll end up with a 4 color plates, each of them consisting of 1/4 of the entire resolution of the sensor. That means we only have a quarter of the blue information from the entire sensor, and a quarter for red. And since we have 2 groups of green, we have half the green information from the entire sensor. This is what is called mosaicked raw sensor data. We can save them, but it is not a complete image. It's not right for viewing. To make a complete viewable image, we have to have the green and red and blue information for every single pixel. So we have to come up with a way to calculate those values for the pixels that they don't have them from the pixels that have them. That process is called demosaicing. Going back to our table of Bayer filter blocks, if I want to find or address each of these cells in the table, I can name them or index them based on their position. Say we index each column with the letter M. If this is column M, the one after that will be column M plus 1, and the one before that will be M minus 1, and the one before that M minus 2, and M minus 3 for the one before. And so the one after M plus 1 will be M plus 2, and the one after M plus 3, and M plus 4 for the one after, similar to door numbers of houses on a street. So in this column, every cell is a member of column M. Equally, if we index rows with the letter N, this will be row N, and row N plus 1, the one after, N plus 2, the one after that, N plus 3, and the one after that, N plus 4. And obviously, the one before N is going to be N minus 1, and N minus 2 for the one before, and N minus 3 for the one before that. Every cell in this row belongs to row N, and we know every cell in this column belongs to column M. Therefore, if I want to address the red cell in the intersect, it's going to be red of column M and row n. So I can write its name down as red of column M row n, or RMN. Similarly, that green cell belongs to column M-1 and row N-2. So I can write its name down as green M-1 N-2. For this blue, it belongs to column M+1 and row N-1. So I can write its name down as BM+1 N-1. If we compare this with the main figure in Red's patent document, figure 3, we'll notice all that Bayer patent blocks, and we'll notice that indexing. That's M for the columns and N for rows. So that red cell in the intersect is called RMN. It's just like giving coordinates on a map. Now, down to the so-called patentable novelty on the Redcode patent. So keep up, the crazy math is coming into the play. Take that red cell in the intersect. The address for that red cell is RM-2N-2. That's only because of where it sits. That red is surrounded by 4 greens. The address for the top one is GM-2N-3. The one on the right is GM-1N-2. The one on the left is GM-3N-2, and the one on the bottom is GM-2N-1. Because these green cells sitting in a very close proximity, it is unlikely for them to have a drastically different values. So instead of keeping all 4, we take an average of them. To calculate the average of these, we add these 4 up and divide them by 4. This is called green average. And to make the numbers even smaller, we subtract this average from the red value and call it red prime. This is called green average subtraction, or GAS for short. So we take the average of 4 greens and subtract it from the red to make a smaller number. That elementary school operation is the crazy math. That's it, folks. But wait, you say, this can't be this silly. There must be more to it, right? Let's check the documentation. This is Red's patent document. Well, remember that the entire Red's family of patents are based on these provisional applications that were filed in April and December of 2007. And the patent examined by Trung Dip. This figure 3 is the key illustration that describes the patent's claim, which is what we have discussed. You'll notice the Bayer color filter cells with blue, red and double green, but instead of color they have the letters. And you'll notice the indexing with letter M for the columns and letter N for the rows. Figure 4 illustrates a single cell, typical for Red, the shuffled a few placements. In figure 5, we'll see one red cell with its neighboring green cells, and in figure 6 we'll see the same thing for a reduced number of green cells. Figure 7 is also an illustration of what we have discussed about the 4 color plates, with each of them being 1/4 of the resolution of the entire sensor. This one is what every digital camera has: a sensor to obtain the image data and something to process that and apply the compression algorithm. And these 2, let's come back to them after we read the claim. And here is what the patent claims. You'll notice that because Red didn't have much to say, they used a complex sounding language to describe something very simple. It reads, in some embodiments, an average value of the data values of plurality of adjacent green picture elements can be subtracted from the red or blue image data value. For example, average value of 2, 3, 4 or more green image data values can be calculated and subtracted from the red or blue picture elements in the vicinity of the green picture elements. Sounds quite complex, right? Let's read the rest in a slightly simplified manner. With reference to figure 3, the raw output for the red element R is surrounded by 4 green picture elements, G on the top, G on the left, G on the right and G on the bottom. Thus, the red element R in the middle can be transformed by subtracting the average of the values of surrounding green elements as follows: green 1 plus green 2 plus green 3 plus green 4 divided by 4, that's the average green, subtracted from red in the middle, that's the average green subtraction, equals to R prime. Oh, the prime symbol is missing in this print. That's exactly what we have seen in our description. Similarly, for the blue element in the middle, we get the average of the 4 surrounding green elements and subtract it from the blue and call it blue prime. That is green 1 plus green 2 plus green 3 plus green 4 divided by 4 subtracted from the blue. Now, going back to that 2 pages that we set aside, we'll see on figure 10, that's the same calculation just put in the table. R prime at a location is equal to R of that location minus the average of 4 surrounding greens. And figure 9 is the same for the blue element at one location. Blue prime at location is the value of blue at that location minus the 4 green elements surrounding that blue. And evidently this primary school level mathematics can make some people inventors. Now you say, maybe this is not the key part. Maybe this is just a bit of a bigger process. Let's see what Graham has to say himself. To get that, I'll go to the case of Apple versus Red.com, where Thomas Graham Nattrass issued a personal declaration in support of the patent. Who is Graham Nattrass? Introduced himself. I am a lead camera system architect at Red, the assignee of the 299 patent and 314 patent. I'm also a listed inventor on the 299 and 314 patents and an inventor to over 25 additional issued patents assigned to Red. These are the family of the Red's patent that each is granted based and in continuance to the previous one. Further down, he describes the 4 phases on how Red camera works and where the patent and the invention lies. He says, accordingly, my work on the Red 1 camera was based on a video image processing pipeline that did not include a conventional demosaicing step prior to compression. Rather, the data flow upon which I based my research and design work for the Red 1 camera generally operated along the following 4-step sequence for processing and compressing raw Bayer pattern video image data. First, raw image data was collected by the image sensor, which was a Mysterium CMOS image sensor chip with a Bayer pattern pixel filter. This is wrong because Bayer pattern does not filter pixels, it filters colors. So what he was trying to say is Bayer pattern color filter. He describes it as a sensor chip that detects only one data value for each of the green, red, and blue pixel locations. This is also wrong because if it was detecting only one data value for each green and red and blue pixel, every frame would have looked the same. What he was trying to say is that this is a sensor chip that detects the data for only one of the green, red, or blue colors at a pixel location. The raw mosaic data was outputted by the image sensor at a resolution of at least 2K and at least 23 frames per second. Second, the raw Bayer pattern image data was then sent to a Xilinx processing FPGA chip for pixel correction and processing of the raw Bayer pattern image data. Third, the pixel corrected and processed raw Bayer pattern video image data was then sent to analog devices compression chips, which utilized a mathematically lossy wavelet compression codec known as JPEG 2000 to compress the processed raw Bayer pattern video image data. This next part is where Graham states that's the key part where the patentable novelty rests. He declares, much of my research and design work that went into the Red 1 focused on the second step above. That's processing the image data before compression. He says, this was a key step in Redcode. It carries on, I ultimately devised 2 methods in particular that were employed on the Red 1 cameras, referred to as GAS or Green Average Subtraction and preemphasis. And he describes the distinguishing key steps. The GAS process technique uses an averaging of green pixel values to produce low noise co-cited estimated green values. How? In the GAS method, green pixels located adjacent or in close proximity to a target pixel are averaged to calculate an average green value, which is then subtracted from the value of the target pixel, whether the target pixel is red or blue. So it's the key part of Redcode. It's the entire point of this patent. As for the compression itself, the patent document says the compression module can be in the form of a commercially available compression chip that performs a compression technique in accordance with JPEG 2000 standard. That is what was used, or other compression techniques. But to cover more grounds without saying how, the patent documents carries on, the compression module can be configured to apply any known compression technique such as, but without limitation, JPEG 2000, Motion JPEG, any DCT-based codec, and to make sure nothing slipped through their fingers, they throw any codec designed for compressing RGB image data, H.264, MPEG-4, Hoffman, or other techniques. So when Apple challenged Red patent, Graham, the inventor, confirmed that the key to the patent is GAS, which he claimed was the only patentable novelty. Analog Devices is a semiconductor company with a long history in manufacturing wavelet-based video compression microchips and one of the main contributors in JPEG 2000. In about April 1996, Analog Dialog publishes an announcement for an arrival of a new video compression chip, ADV601. On page 7, we read the ADV601 is a low-cost single-chip, all-digital dedicated function CMOS VLSI chip for compression and decompression of digital video signals in real time. The chip codec algorithm is based on a bi-orthogonal wavelet transform embodied with 7-tap high-pass and 9-tap low-pass filter. It says it's based on a wavelet theory, a new mathematical tool first explicitly introduced in works on geophysics during the mid-1980s. In April 1996, even before JPEG 2000 exists, this was labeled as industry's first integrated wavelet video codec that was meant for broadcast quality applications such as nonlinear video editing, video capture systems, and camcorders, among other things. After JPEG finalized the JPEG 2000 standard back in year 2001 with a heavy contribution of Analog Devices, Analog released a new set of JPEG 2000 compliant ICs such as ADV202 and ADV212, which were designed for professional production applications such as professional camcorders, HDTV video editing, and most important of all, digital cinema. Why do we care? Because on the Red One's motherboard there are 6 ADV212 chips. ADV212 datasheet tells us that's made for high bandwidth image compression applications such as digital cinema systems. And despite Graham's declaration that said the idea of compressing single component was his and that JPEG 2000 compression was meant only for 3-component demosaicked image data, the datasheet confirms that the ADV212 is capable of processing up to 4096 pixels in a single component mode. That's the DCI's 4K pixel size in a RAW. Further down, the datasheet confirms that the chip is capable of processing single or 2 or 3 components input format. So compression technology was not new. The idea of compressing a single component image data, raw image data, was not new. What about the treatment of getting the green average? To just get you an example, in October 2006, that's even before the Red's first meeting according to Jim Gennard, DesignLine, a specialist publication in signal processing, published an article about JPEG 2000 codec. At some part it reads, developed more than 6 years ago by the Joint Photographic Expert Group, JPEG 2000 has gradually become more prevalent in a variety of industries such as surveillance, medical, satellite, and more recently, professional video including digital cinema. But at the time, Red didn't exist. So who was using it in professional digital cinema?
So we had started sort of the early revolution of what is now digital cinematography, because previously cameras were 3-chip, that was considered the professional. It had 3 CCDs and a beam splitter and a blip, to break up the RGB light and encode it separately. But that prevented the lenses getting bigger and getting to the sizes that they used on film. And once you could compress a large sensor image natively in the original sensor format, and that's what we just invented at CineForm. And then we've seen that world explode, and now single image, large sensor is the commonplace.
David Newman, founder and chief technology officer of CineForm. CineForm is a 12-bit full-frame wavelet compression video codec. It is designed for speed and quality at the expense of very high compression size. Image compression is a balance of size, speed, and quality, and you can only choose 2. CineForm was the first of its type to focus on speed while supporting higher bit depth for the image quality. CineForm video codec was developed in between 2001 and 2002 as a lightweight compressed alternative for DV or other consumer formats of the time. However, around 2003, CineForm HD was developed, which moved the codec from a consumer 8-bit YUV to offering 10-bit YUV and 12-bit RGB and RGBA for professional work. CineForm was ideal for the transition to HD, being a native wavelet codec, because its efficiency improves with the resolution increases, because when the resolution increases, you get more redundant data.
So CineForm started in 2001.
Yep.
Was it the video editing, or was it the codec that was
Well, yeah, we started with this vision that video editing needs to be easier. And the first thing we found the problem was that all the compute resources were taken up with decoding the compression technology that was coming from the cameras. And so what we realized, the reason people couldn't do video editing in real time back in 2001, 2002 timeframe, is the codecs were killing the compute performance. So we didn't intend to be a codec company. We designed the CineForm compression to solve a customer problem that it turned out to drive our business. Everyone loved it. And we also, because of my experience with building screenplay, we used a Wavelet chip there, and I loved the quality of the Wavelets. In compression, there's two camps. There's Wavelet and DCT. Wavelet is used in JPEG 2000, which you may have encountered. But when you get artifacts, it looks soft. It looks a little blurry. And as a result, people don't see it. They're used to seeing the little ringing boxes and the contouring in the sky, and they don't see it. So we could get away with higher compression than our competitors could, and no one would notice the artifact. So I love that, because if I'm going for a consumer market, I don't want to eat up a lot of disk space. But it also had a nice artifact, is that if you increase the bit rate, it never had any macro blocking or edge artifacts, which means the professionals loved it. So we ended up being, even though we had this vision of making video editing possible for consumers, we ended up finding that we were servicing Hollywood and feature films and everything wacky in the world of feature content creations.
CineForm wanted to run their codec on an average consumer PC CPU, but JPEG 2000 has a hefty arithmetic requirements for its compression. CineForm had to create their own adaptation of JPEG 2000 for speed.
I will say that when CineForm was founded, we thought we'd use JPEG 2000.
That's right.
And then we realized, oh my God, this is, yeah, it's a good codec. I mean, there's nothing wrong with Red
It's
Raw.
fantastic codec, but
it's about 8 to 10x more compute intensive than what we ended up
doing. That's right.
doing.
Now, the interesting thing about this is the most interesting thing about this is that you take a 10% hit in size, but it's 8 to 10 times faster, which means you can edit a raw codec in VC5 on a laptop.
Yes.
Huffman coding, on the other hand, is a decades-old method, less compressive but way faster. So CineForm chose Huffman over arithmetic. David Newman took a further step in filtering the input signal. In the wavelet method, the first step is separating the high frequencies from the low frequencies. For example, if the input frequency is like the image at the bottom, it can be separated to the two sets of frequencies shown above. In each one of them, either high or low frequency is passed only. When we add these frequencies, they'll create the original input waveform. The wavelet compressor then treats the high frequencies differently than the low frequency. The JPEG 2K assigns 5-bit and 3-bit out of each byte for the high pass and low pass. CineForm adaptation is 6-bit and 2-bit, which is more compatible with ordinary CPUs. The result is a 10 times faster codec than JPEG 2K for about 10% larger file size. On dvinfo.net was a group called Alternative Imaging Methods. In this group, around 2001 to 2005, people were sharing their experiences of building DIY adapters to stick photographic lenses to CMOS sensors that were mainly silicon imaging machine vision sensors, and recording the raw mosaic sensor output directly onto their hard drives. Eye-catching quality, but a large sensor means large file sizes. David Newman noticed these genius hackers' work and initially, as a hobby, extended CineForm's codec functionality to also compress Bayer pattern mosaic raw output. Why did CineForm choose RAW? Size and speed. Size-wise, if you get raw data, recording it as it is an obvious choice. Underneath the Bayer pattern is a sensor photosites. With the Bayer filter on, each underneath photosites gets data for only one of the R, G or B, but for the full image, each pixel must have all three. So you interpolate to demosaic and give each pixel its RGB for recording. If recorded in mosaic RAW, you had to only deal with red, green, green and blue, whereas after the mosaicing, you will need to deal with 3 to 4 times of data size. This functionality gave birth to the CineForm RAW codec developed before 2005 that went into the Si2K camera. Though the declaration of Thomas Graham Nattrass doesn't mention any of these. Describing their work after December 2005, meaning 2006 onward, he says, "We believed that the benefits of the Bayer pattern image sensor could be optimized if the image data remained in raw mosaiced format for compression." He says, "As I explained before, the typical flowchart for prior art video image data capture involved demosaicing Bayer pattern video data prior to compression." Forgetting about the CineForm, he says, "We rejected the conventional thinking by implementing non-compression techniques such as JPEG 2000 in such a way as to operate on non-demosaiced Bayer pattern image data."
Into your...
Well, yeah, I can talk to that because one of the problems as the resolutions get higher, let's say with 4K P60 from a cinema camera, that's a hell of a lot of data, 12 bits per pixel or 14. Now the problem is that traditional, both intermediate codecs will actually demosaic that data to 444, which is 4 times the amount of data that was on the original sensor, then compress it. So the compression can't be nearly as efficient. So when we developed the CineForm RAW codec, which was the very first part, it's part 1 and 2 of the VC5 standard with SMPTE. That's been filed and published now for about 9 months, I think. And so RAW was the part we focused on because we knew that was the thing that was the most distinguishing thing that made CineForm and VC5 very different from every other codec.
That's right.
And it's, to speak technically, it's still a mathematically lossy codec, but the idea is that you go for a 5-to-1 compression or a 10-to-1 compression where you get your workflow efficiency improves. It's not like a mathematically lossless compression, which would be more like 2-to-1. As our images get bigger, there's more redundancy to exploit. In 4K, you can more comfortably go around 7-8-to-1 and not ever see any artifacts with 12-bit encoding of RAW. So when you go from a RAW image, which might be natively 150 megabytes per second type of thing, down to like 20 megabytes a second, now you see how much your workflow can improve. And because we used wavelets, wavelets have this natural kind of pyramid encoding scheme where you're not always going to have a 4K monitor there. You don't always need to present at 4K, and you begin encoding 6K and other resolutions right now. So you can decode at sub-resolutions at a vastly improved performance. So that was a thing that CineForm developed, I don't know, 10, 15 years ago.
Silicon Imaging was not oblivious. They saw the market potential and came up with a camera product, Silicon Imaging Si2K. The camera implemented CineForm RAW codec. Well, the camera spec says raw digital information from the camera sensor is recorded directly into the CineForm RAW format, which leverages CineForm's respected visually perfect wavelet compression technology. Visually perfect is the CineForm's trademark wording for what Red later claimed as visually lossless about 18 months later. Recording in the CineForm's RAW digital intermediate format records a digital negative direct to disk, preserving full dynamic range and per pixel sensor data in the codec. The 2005 camera brochure describes even more. Silicon DVR records directly to CineForm RAW Digital Intermediate, a powerful 10-bit visually lossless codec that preserves and manages the raw Bayer data at the codec level. And this 10-bit Bayer raw data can be recorded in log. We remember that Graham Nattrass assigned this to himself too. In his declaration he said, pre-emphasis curve changes the gradient in different sensor code value regions. This technique can be used to spread apart pixel values in some ranges and squeeze together values in other ranges, which is some sort of an attempt to take the ownership of the well-known log curve. So nothing in the Redcode was actually new. What about the innovative green average and the 4 color plates? In Redcode, to get red or blue pixel, we need 5 inputs. To get the red number 5, we'll need green number 1, 2, 3, and 4. Then we get their average and subtract it from the red. This covers a large block, so softens the green and produces a bit of color bleeding when demosaiced. Thus, the Redcode's sharpening exists. Graham said no one else did it, right? What about the CineForm? CineForm RAW gets one Bayer cell. It gets the two greens and instead of keeping them both, gets their average. Since the average is sitting right at the intersect of the two greens, it's a very accurate representation of the green value. CineForm also holds the difference of the two greens. Because these two are in a very close proximity, the difference is a tiny number, next to 0. So keeping it doesn't take much memory. But if the difference between the two is significant, it means that we are looking at an edge of something. The result is a sharper image, and if more sharpening needed in the post, the edge data is preserved. To get red pixel, CineForm gets the green average and subtracts it from the red. So it needs 3 inputs for it, and the same goes for the blue. In the end, it results into 4 color plates. The only difference is that red changed the number of elements in green average calculation. And what about the 4K resolution? Well, this process of taking an average and subtracting is resolution independent. JPEG 2000 is resolution independent. So obviously this can be applied to any resolution.
The most common use case is IMAX. Because even when they were still shooting IMAX film and they were scanning the IMAX negatives at like 8K, well, what are you going to store that in? An uncompressed 8K frame. And a frame is 152 megabytes or something crazy like that. And then if you're doing 24 frames a second, and IMAX sometimes run at 48, and just the burden of data is massive. And IMAX films have limited budgets. I mean, they're not, if a film makes $10 million as an IMAX film, it's a blockbuster. So they can't afford to even store their film. So they needed to look for a compression solution that would preserve the quality, because IMAX is the premium in quality, and we're the only one, even today, practically. So we're still using IMAX features.
In the next video, we will see all the reasons why this patent is invalid and where did Apple get it wrong. Creating this content is difficult. Please show your support, like and subscribe.
We can do everything that we've talked about doing in software. So when we founded CineForm, which was founded from the engineers from Applied Magic, so really it's like it was an evolution. We got new VC funding, and we made an organization that says, we're going to solve consumer.
We have no idea. I've said this before, said this, and it's true. We have no idea whatsoever what we were doing now. No idea. We're making it up as we go.
Off-the-shelf compute hardware. So we would just be a software company. And that was the vision. It didn't turn out that way, but that's what we intended to start.